Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Atoms, Molecules and Nuclei. Now, let's see Davison's and Germer's experiment. And Germer's experiment. They experimentally proved the dual nature of matter, that matter exists both in particle as well as wave form. Now let's see the construction of this. You have an electron gun, that's your heating filament, to which a DC source is connected. This is then you have two plates to streamline the beam of electrons, which is streamlined to be ejected and hit on a plate, on a nickel crystal plate. This is the nickel crystal plate on which it is going to hit. This is the enclosure for it. Now, as the electron beam emitted from the filament hits the nickel plate, it is going to get reflected, right? Let's assume that you have a circular scale that is connected over here. Right? You have a circular scale that is connected over here. Right? Here you have a device wherein you will be able to measure the intensity. You have this device that is connected here that would enable you to measure the intensity of the reflected electrons. Right? How would it do that? How would you know the intensity? By connecting the other end to a galvanometer, extremely sensitive galvanometer. Right? So electron beam would hit the nickel plate and would be reflected onto this collector. Right? That's your construction of this. Let's see the apparatus. I can say that it consists of an electron gun that produces the electron beam. We'll call this G to be the electron gun. So an electron gun produces an electron beam right? The electron gun consists of a tungsten filament which is heated. The electron gun consists of a tungsten filament which is heated. Right, the tungsten filament is heated and electrons are emitted from the filament by thermonic action, which is heated to emit electrons by harmonic action. Electrons are going to be emitted due to harmonic action. These electrons are going to be accelerated in the electric field of known potential difference and culminate through suitable slits so that they emerge in the form of a fine pencil stream. I want the electrons to emit in the form of stream. So electrons are accelerated in an electric field of known potential difference and culminated into a fine stream, culminated by narrow slits, by suitable narrow slits to give a fine stream of electrons. So now through the electron gun you have the stream of electrons coming out. Now this beam is directed finally to fall on the target, which is a large crystal nickel. This is my target T, right? The beam falls on a large crystal of nickel. Now, this particular target can be rotated about the parallel axis to the incident beam so that I can direct the beam in the direction that I want. So I can say that the target can be rotated about an axis. The target can be rotated about an axis parallel to the incident beam. Right? Now, the electrons acting as a wave are scattered in all directions by the atoms in the crystal, and they are allowed to enter a cylinder called as the collector. This here is the collector. Okay. I can say that the electrons acting like waves, are scattered in all directions by the atom, by the atoms in the crystal. And are allowed to enter a Faraday cylinder called as the collector, and are allowed to enter a Faraday cylinder called the collector C. Okay, once the electrons are in the collector is connected to a sensitive galvanometer and can be moved along the graduated circular scale. The collector is connected to a sensitive galvanometer and move along the graduated scale. Fine. So as to receive the reflected electron between angles of 20 degree and 90 degree. So as to receive electrons between angles of 20 degree 90 degree. Fine. Okay. Now the deflection of the galvanometer is directly proportional to the intensity of the incident electron. Higher the intensity of the incident electron, more will be the deflection in the galvanometer. So I can say that the deflection of the galvanometer is directly proportional to the intensity of incident radiation. So now we have the electrons that are collected, right? The collector has two walls insulated from each other, and the retarding potential is applied between the inner walls of the collector. You have two walls. If you see the collector, there's an outer wall and the inner wall. Now there's a retarding potential that is applied to the inner wall of the collector, so that only those electrons that are fast enough should be able to enter. The scattered electrons should not be allowed to enter the collector. Only those electrons which have sufficiently high velocity can enter the collector. Fine. Okay. Now the whole apparatus is completely enclosed in a highly evacuated degas chamber. The whole apparatus is enclosed in highly evacuated degassed chamber. Right? Now once you have this, now for normal incidence, the beam of electron on the surface of the nickel crystal, the electrons are going to be scattered in all directions and will behave like a wave. Once the beam of electron hits the nickel, these electrons are going to be scattered in all directions. They will behave like a wave. The collector is then moved to various positions along the graduated circular scale so as to collect these electrons, right? The current in the galvanometer will tell me the intensity of the electrons that are going to be collected by the collector, right? So it will, in a way, it will go on telling me the intensity of the diffracted wave. Higher the current moving through the galvanometer, higher is the intensity of the diffracted wave there, right? And then I can draw a graph and find out whether the particle has dual nature, right? That's how the experiment is conducted. Let's write the experiment now. I can say that the electrons are scattered in all directions. I can say that the beam of electrons after colliding with the nickel crystal will cause the beam of electron after colliding with the nickel crystal will have the electrons scattered in all directions, indicating that they behave like a wave. Had they not been behaving like a wave, they would have been reflected in a beam-like manner. The fact that they are scattered in all directions indicates that they behave like a wave, scattered in all directions, indicating that they behave like a wave, The collector is moved to various positions on the scale. The collector is moved to various positions on the scale and the galvanometer current indicates the galvanometer current indicates the intensity of the diffracted beam. The intensity of the diffracted beam. So I would know the intensity of diffracted beam, right? So a graph of galvanometer current versus the angle between the incident beam and the scattered beam entering the collector is plotted. Now this angle between the incident beam and the scattered beam, the angle, guys, the angle between the incident beam and the scattered beam, this particular angle is called as colatitude. This particular angle is called as colatitude. That means you are going to now plot a graph of galvanometer current versus the colatitude. Okay, that is your angle between the incident beam and the refracted beam. Now I'm going to draw the graph and show it to you. Conclusions. Now you have a graph that would be like this. This is the graph at 44 volts, right? This is my incident beam. The incident beam is moving straight this way. The refracted beam should have moved either in the straight angle or in a particular angle. If it did not have dual nature, it should have moved only in one angle. Now see how the reflected beam moves. It moves this way, right? Now if you consider this mean angle here, you will see that the angle between the incident beam and the reflected beam is 50 degrees, right? Now suppose if I increase the potential at 48 volts, remember you were guiding the electron beam with the help of potential. So if I increase the potential from 44 volts to 48 volts, this is my incident beam. Incident beam coming down. Now at 48 volts, you will see that the wave structure is more. Then it will move up. It will still be at this angle of 50 degree only. The angle between the incident beam and the reflected beam is still going to be 50 degrees only. Now if I increase the potential from 48 volts to say 54 volts, this is my incident beam. You will see that the movement is more pronounced at 54 volts. The angle still remains 50 degrees. The angle between the incident beam and the reflected beam. Now suppose if I increase this potential to 60 volts, right? Here you can see that the magnitude of the beam or the amplitude of the beam has increased from 44 to 48 to 54. Now suppose if I increase the potential to 60 volts, this is my incident beam moving down here. Let's assume I increase the potential to 60 volts. You will see that at 60 volts the amplitude of beam the amplitude of the wave will decrease. So the amplitude is maximum at 54 volts. It starts to increase from 44 volts, it increases to 48, it becomes maximum at 54, and after that if I increase, it decreases. So this is going to be 50 degrees. Right, do we understand this? So do you understand the colatitude angle is going to be 50 degrees. Now at 50 degrees, you observe this kind of pattern where the intensity increases to show that the amplitude of the wave is going to go on increasing. Let's write this down, guys. I can say that the graphs indicate that first, the intensity of the scattered electron depends upon the angle of scattering. The intensity of scattered electrons depend on the angle of scattering. You will see that all the angles, all the graphs that we've drawn are drawn at 50 degrees. Next, you will see that a bump begins to appear on the curve at 44 volts. At 44 volts, a bump begins to appear in the curve for 44 volts. Right now, the bump is found at a colatitude angle of 50 degree. This bump is maximum at the colatitude angle is written as 5 at 50 degree, right? Now, as the accelerating voltage is further increased, the size of the bump goes on increasing. As the accelerating voltage is further increased, the size of the bump goes on increasing. Right, so the size of the bump would go on increasing, and it is the greatest at 54 degrees. The size of the bump is greatest at 54 volts and at a colatitude angle of 50 degree. Fine. That means the intensity of the diffracted beam is strongest in this case, right? Now, if the accelerating voltage is further increased, as the accelerating voltage is further increased, if the accelerating voltage is further increased, the bump starts decreasing in intensity and finally disappears at 68 volts. The size of the bump starts decreasing and it finally disappears at 68 volts. Fine, do we get this in here? Now, this size of the bump and the colatitude angle and the potential at which the bump appears enabled Davison and Jaumer to come up with a formula. They came up with a mathematical relationship for this particular graph. They came up with a relationship, I can say that the mathematical relationship he said that n lambda is d times sine phi, where lambda is the wavelength of the electron, n is the order of maxima. Remember from your interference of light, when you have diffraction, the central maxima, then you have minima, then you have first order maxima, second order maxima. So this is my order of maxima. Which maxima am I looking at? D is the interatomic distance of nickel atom. Interatomic distance of nickel atoms, and phi is the diffraction angle. Now, for nickel the interatomic distance, but D, that is the interatomic distance for nickel, has been found out to be 2.15 Armstrong unit constant. We also have seen that the experiment was done when the diffraction angle was 50 degrees. Since the intensity of the bump went on increasing, that means the order was the first order. I was looking at the first maxima. Now if I substitute all this, what I will get is the wavelength of the electron. If I substitute this in the equation, I'll get 1 lambda is 2.15 into sine 50. When you solve this, you will get the value of lambda as 1.65 Armstrong units, right? Because D was in terms of Armstrong unit. Now, if once I know the wavelength of the electron, I can use this wavelength in de Broglie's hypothesis. So I can say that, but by de Broglie's hypothesis, if I apply de Broglie's hypothesis, we know that lambda is 12.27 upon square root of V Armstrong units. Now we know that the intensity of the bump was maximum at 54 volts. So if V is 54 volts, we will get the value of lambda as 1.65 Armstrong unit. That means Davison and Germer's experiment further goes on to prove de Broglie's hypothesis that the wavelength of the electron is going to be 1.65 Armstrong units. Fine, do we get this thing clear? Next, let us see the working of an electron microscope. First, let's see the idea of an electron microscope. Now, we have learnt that the resolving power of an optical microscope increases with the decrease in the wavelength of the light. As the wavelength of light goes on decreasing, the resolving power of an optical microscope goes on increasing. That means the distance between two objects which have to be resolved will be easily resolved if the light is of smaller wavelength. The smaller the wavelength of light, the further away the two distances which are close to each other will appear, right? Hence, now there's a problem here. There's a limitation to the minimum wavelength that can be used in the visible and the ultraviolet spectrum. I could use light in the visible spectrum, or I could use light in the UV spectrum. But even if I use light in UV spectrum, there's going to be a limitation to the minimum wavelength of light. I cannot change the wavelength of light even in the UV spectrum. For a particular color, you would have a particular wavelength only. I cannot change that wavelength. Therefore, I can say that the calculation with visible and UV light suggests that there is a minimum distance at which two objects should be placed so that they can be easily resolved, because it is the wavelength of light that will help you resolve. I have a certain limitation to the wavelength. Now for that particular wavelength, only if the objects are placed at a certain distance from each other will they get resolved, right? Which works out to be 200 nanometers. That means if two objects are placed at a distance of 200 nanometers, then by using light in the visible or the UV spectrum, I can resolve these two objects. But this is a limitation of my optical instrument. Now, do you understand this? Suppose if an electron is accelerated with a potential of 50,000 volts, hypothetically, let us consider, then it produces a wavelength of 0.0055 nanometers. If I accelerate an electron with a potential of 50,000 volts, I can produce 0.0055 nanometers of wavelength. Now, this wavelength is far smaller than the wavelength that I can get from visible or UV spectrum of light. Since the size of the wavelength has reduced, that means the resolving power of the optical instrument would increase in that case, right? Hence, and a device that uses the electron wave for resolving the distance, for resolving an object, is called as an electron microscope. So what is such a device where you would have, say, an electron beam accelerated with 50,000 volts that would produce a wave. That wave would have a wavelength very small, and that small wavelength would help me resolve two objects which are extremely close to each other. Right? Do you understand this? So particles such as electrons have wave nature, and they also have the nature of light. They have dual nature. We are going to make use of both the properties here. So hence an electron, since it has it behaves like a light ray, it can be easily focused in a suitable magnetic and electric field, right? And since it has a wave nature, it can behave like a glass lens, which will help me resolve the object, right? So do you understand this? So do you understand the idea of an electron microscope? Why do I need an electron microscope? Because if I use a microscope using the UV light or the visible light, the maximum distance that I can resolve is 200 nanometers. But if I want to resolve a distance of more than 200 nanometers, I need a light which has wavelength less than the light that is present in the UV spectrum or the visible spectrum. And this particular wavelength can be achieved only with the help of an electron. Right? Do you understand this? So let's see an electron microscope. Now an electron microscope is made up of two categories. It is made up of an electrostatic category and a magnetic category. The electrostatic category is used for producing electrostatic lens system that will help in focusing the electron beam. The magnetic is used for magnetic lens system. So you would have two different types of lenses that would be formed in the case of an electron microscope. Fine, do you get this thing here? Now, furthermore, electron microscopes can be classified into two categories: emission type and transmission type. What are emission type electron microscopes? These are the ones in which the magnetic image is simply reproduced. Magnetic image is a simple reproduction of the surface of the cathode and from the source of the electron. So you would have just reproduction of the image. A transmission type would magnify the image and produce it. Now I'm going to show you how to make a transmission type electron microscope. Fine. Let's see first the diagram of an electron microscope, and I'll show you how it works then. First of all, if I need an electron microscope, I need a beam of electrons. A beam of electrons can easily be produced with the help of an filament. So first thing I need is a filament. The filament would be heated only when I apply a DC source to it. So a DC source is applied to the filament. In order to control the speed with which the electrons will move and the thickness with which the electron will move, I need to have a system that will streamline them. So what I'm going to do is, I'm going to put in a system here. Of variable potential difference. Right? So this is the electron gun. The first thing that you have is the electron gun. This is my focusing system. So now you have a thin stream of electrons coming out from the focusing system. Now, on either side, yes, you have a thin stream of electrons coming out from the focusing system. Now, on either side, you would have a magnetic field that would be produced, right? So I have a magnetic field produced here. To produce this magnetic field, you have coils inside here. Right? Due to the magnetic field that is produced here, the beam of electron that is going to emerge initially would get scattered. The beam of light that is coming out from the focusing system would be scattered. This magnetic field would streamline it. I will show you its equivalence in an optical system also. So this particular system of magnetic field that is produced is called as a magnetic condensing lens. The magnetic field here acts as a convex lens, right? So these are your magnetic condensing lens. This is your magnetic condensing lens system that has been formed with the help of the magnetic field that is produced, right? Now, at the end of this, you would have an object that would be placed, right? I would have an object that would be placed here. This is the object that is placed here, okay? This is my object O, which has been placed in the path of this beam, okay? Then I would have a system of another lens which would be formed with the help of magnetic fields. Right? So you would have another magnetic condensing lens. Now this would be called as the magnetic objective lens. This particular lens would be called as the magnetic objective lens. Right? What would this do? This would focus the beam of light in such a way that the beam of light would move in opposite direction and I would get a magnified image. I would get a magnified inverted image. I would get a magnified inverted real image, right? Then I would have another system of magnetic lenses, right? So you would have a third system of magnetic lenses here. my third system of magnetic lenses. This is called as magnetic projection lens. This is my magnetic projection lens. Right? This would further magnify the image. This would further magnify the image. And finally, I would get a magnified erect real image on the photographic plate. Right? This would be my image, final image on the photographic plate. Final image on photographic plate. That would be my final image that would be formed on the photographic plate. Now I could show you the equivalence of this in the case of a lens system, wherein I would have a source. This is my source of light. Right, I would have had a source of light. I would have kept a lens in front of it. The equivalence of this would have been a lens that would have been kept here, a convex lens. The source of light would have given out light, which would have light. This was the light that would have been given out from the source, right? Which would pass through the convex lens and would converge. So that would give me the image, and I would keep an image in its path. So if I kept an image in its path, this would be the image that would be kept in its path. So you would have source of light that would converge and pass through the image. Right? And I would have another lens that would be placed here. This is the second lens I would have here. From here, the ray of light would further move out. That would give me an image here. I'm showing you the equivalence in the case of a lens system, right? Which would again get converged. You would have a third lens that would be placed here. Right? And that would give me my final image. This is how, in the case of a lens system, it would have worked. Right? Where this is my condensing lens. Here we are producing the condensing lens with the help of magnetic field. This is my object O. This is my objective lens. This is my projection lens. And this is your final image. Right? That would have been the working of your electron microscope. So you would have the electron gun. In the electron gun, a stream of electrons will be produced with the help of the filament. Guys, can you just listen to this? From the electron gun, you would have a stream of electrons that would be produced by the filament. The filament would produce a stream of electrons. The beam is accelerated with a potential of 50,000 volts. The 50,000 volts potential is produced from there. Now the beam is focused onto the object. This is the beam, it's coming out from this focusing system. It is focused onto the object with the help of the first magnetic condensing lens. Right? Now, the magnetic condensing lens act as an condenser lens of an optical microscope, and they are produced with the help of an electromagnet. Right? You have electromagnetic field that would produce the same effect as that of a condensing lens. Right? The contracted beam falls onto the object. The contracted beam falls onto the object, and the object is magnified. Right? The object is placed on a very thin system which is about 10 millimicron thick, so that the light beam can pass through it in a special holder. Right? Because some of the electrons that would strike that filament on which the object is placed would be stopped by that filament. Hence, it has to be placed on an extremely thin filament. Okay. Now, then you have other objective lens that is produced by the magnetic field, right, which is called as the magnetic eyepiece. This would further magnify the image, and the image would get magnified with the projection lens system, and finally you would have the image that would be produced on the photographic plane. And do you get this thing here? So do we understand how an electron microscope works? Reason why do I need an electron microscope? As I already told you, it produces an extremely high order of magnification. It can be used to focus on very fine objects, right, which can be easily resolved with the help of an electron microscope. Fine. So do we understand this? This finishes this chapter. We'll stop this here for the day. Thank you very much.